All right, so an additional improvement that we can add to the multiple regression model to help it to better accurately reflect reality is to add what's known as interaction variables. Now, fair warning on this takes a little bit of time to digest because at first glance, you'll probably be like, whoa, okay, what's actually going on? So I'll try to go over it a little bit slowly so we can understand the huge advantage we often get by actually adding these type of variables into the model. So far with the multiple regression equation, we've assumed that the effect of x on y is a constant, regardless of the other values of the predictors. So with the salary data set, we've fit a model predicting salary from education, experience, and months. So if we think back and if we just try to predict salary from education and experience, that's what we've done in the multiple regression model. However, there might be a fundamental flaw with trying to model salary that way. Because what our multiple regression model assumes is that the difference in the average salary between two people with, say, identical levels of experience but differing levels of education is always a constant. So, in other words, imagine that our multiple regression model had the coefficient of education to be 100. What we would say is that two people that differ in education by 1 year, but whose levels of experience are the same, are expected to differ in salary by $100. Now, in our interpretation, implicitly, we're assuming that's true regardless of the actual value of that person's experience. So, two people that differ in education by 1 year but who have no experience are expected to differ in salary by $100. Two people with 20 years of experience but who differ in education by 1 year are still expected to differ by $100 in salary. Now, that's probably not actually the case because the strength of the relationship between salary and education probably changes depending on how much experience someone has. So, for example, for someone with no experience, the amount of education is probably very important when determining salary. So if we compare two people with absolutely no experience, the person who's probably more educated receives a lot bigger of an increase in their salary compared to the person with no experience and no education. However, if people are really experienced, their education is nearly irrelevant. If we look at two employees that have 20 years of experience each, and one of them happens to be 1 more year educated than the other, well, they probably don't have as large of a difference in salary than if we were comparing these two individuals and they both had no experience. So, in other words, the strength of the relationship between salary and education depends actually on how much experience they had. And that's not an effect we can capture in the multiple regression model as is, because we assume that regardless of someone's experience level, the difference in the average salary based on a difference of 1 year of education is always the same, regardless if they have no experience, 20 years of experience. The difference in average salaries when two people differ in education by 1 year is a constant. All right, so if the strength of the relationship between y and x depends on another quantity, we say that those variables have an interaction. And what I mean by strength is I really mean the coefficient of that variable. And so specifically, we're going to say that when the value of the coefficient of x1 depends on another variable x2, those two variables have an interaction. And very often, that's how the real world is going to work. The effect of y and x is not a constant, but varies depending on a third quantity. We're going to have to incorporate interactions into the model. So how do we do that? Well, we can actually do that by adding an additional term into the multiple regression model. If x1 and x2 have an interaction, we add in a third term, which is the product of those two variables. So how does that allow us to capture an interaction? Well, it's a pretty ingenious move, and let's see how that actually works. So let's imagine that we're looking really at the relationship between y and x1. And let's just group terms in this equation. Well, beta 0 and beta 2 x2 can be grouped together because they don't depend on x1 at all. And beta 1 x1, beta 3 x1 x2 can be grouped together. I can take out that common factor of x1, and what I've left over I can group together here. So if I look at this equation, my multiple regression equation just written a slightly different way, I see now that the slope of the regression relating y and x1 actually depends on the value of x2. That slope is going to get bigger or smaller depending on x2. So for instance, let's imagine that x2 is equal to 0. Well, just plugging in 0 wherever I see x2, my regression equation would be y equals beta 0 plus beta 1 times x. Now, if x2 is equal to 1, plugging in 1 wherever I see x2, I would find that y is equal to this plus beta 1 plus beta 3 times x1. So what I see now is that the slope of the regression relating y and x1 actually varies depending on what the value of x2 is. It might be stronger, it might be weaker, depending on the signs of the coefficients, but adding in this extra term allows me to model the possibility that the strength of the relationship between y and x1 may not be a constant. So we'll talk about how we do that in R a little bit later. But let's talk about what we can do with an interaction, how we can learn what the interaction is telling us. So when we fit an interaction in the model, what we often do is we look at the model's implicit regression equations. So what the implicit regression equation is just a special case of the multiple regression equation when one or more of the variables take on fixed or known quantities. So for instance, we started out with that multiple regression equation, having that interaction between x1 and x2. And on the previous slide, we plugged in the value x2 is equal to 0 to obtain this equation. This equation is what I'm going to say is an implicit regression equation. It is the implicit regression equation relating y and x1 when x2 is equal to 0. Going back 2 slides, this would be the implicit regression equation between y and x1 when x2 is equal to 1. So it's the equation implied by the multiple regression when one of the variables assumes a particular quantity. Okay, so let's explore the interaction between education and experience in the salary model. So here I fit the model with the interaction. Here's the interaction term. Here's its coefficient. And here is the p-value. It's 1%. So we see that the interaction is statistically significant. So adding this interaction term into the model that already contains education and experience significantly decreases the sum of squared errors. So my model improves by considering this interaction term. So let's write out some implicit regression equations just to see, well, what does this interaction being present imply about the relationships? So just translating the coefficients that I see here to the multiple regression equation, let's write out the implicit regression equation between salary and experience now. Actually, let's stick with the relation between salary and education, which we've been talking about. Here's my multiple regression equation. And let's write out the implicit regression equation when experience is equal to 0. So we're comparing two individuals who are complete newbies. They have experience of 0, but they differ in education by 1 year. Okay, well, plugging in experience equals 0 here and 0 here, these two terms go away because they're just zeros. And my implicit regression equation is that salary is 2842 plus 150 times education. And so the implication is that two individuals that differ in education by 1 year, but whose experience levels are 0, are expected to differ in salary by $150, the more educated person having the higher salary. Now let's imagine two people that are very experienced, have experience equals to 20. Well, I plug in 20 where I see experience here and I see experience here, and then just group the like terms. 2842 plus 38 times 20 is 3602. 150 times education minus 6 times education times 120. 150 minus 120 is 30 times education. So the implicit regression equation says that, okay, two individuals that differ in education by 1 year, but who have 20 years of experience, are expected to differ in salary by only $30. So sure enough, my guess looks to pan out from the data. I suspected that the effect of education diminishes when someone is more experienced because, after someone has a tremendous amount of experience, the company probably doesn't really care how educated they are. They know they can do the job. So what we see is that education has a fairly large effect on salary, when experience is very small. The amount of education is a very good predictor of salary in that case. But the effect diminishes for larger experience levels. The coefficient is much smaller, closer to 0, implying that education has much less of an effect on salary when experience is large. So when we fit an interaction into the model, very often we recover some of the implicit regression equations so we can tell a story for how the effect of y and x1 varies on the value of x2. All right, I'm going to skip these slides for now because I actually want to talk about the interaction plots of the model, because for those of you who aren't comfortable working with the equations, the interaction plot actually will show you what those implicit regression equations are for 3 values of the other variable, that third variable. So the command is interaction plots, and it's going to take a fitted regression model. So let's look at the interaction plots for the salary data. So we already did this analysis numerically and with equations. Visually, this is what the analysis would look like. So we're looking at the relationship between salary and education. And let's look at how the implicit regression equations are for 3 different values of experience. The smallest value of experience in the data, the solid line, the median amount, the dashed line, and then the maximum amount of experience in the data, the dotted line here. So for people with the minimum amount of experience, here's the relationship between salary and education. It's very strong and positive. Now, as someone's experience level increases, say from the minimum to the median, this line changes from going like this to this dashed line. So we see that the slope of this dashed line is smaller, it's closer to 0, implying that as people's experience levels increase, the effective education diminishes. The slope is getting closer to 0, and so experience is getting less important. Now, as I move from the median experience to the maximum amount of experience, what I see is this line kind of goes tilted, it gets closer to 0, the slope being 0. Eventually, the effect of education on salary completely disappears somewhere between the median and the maximum. And by the time I reach the maximum levels of experience in this data set, it actually looks like the relationship is a little bit negative. It looks like the more educated someone is, the smaller the salary actually is in the company. That's what the data is saying, a little bit intuitive, but that's the story behind this interaction plot. As experience gets bigger, this line is kind of tilting closer and closer to having a slope of 0, implying that the effect of education diminishes. Now I could look at the interaction from a different angle, looking to see how the relationship between salary and experience changes depending on someone's education. Well, when someone has the minimum amount of education here, this solid line, we see that salary and experience have a fairly strong positive relationship. Now, same kind of thing going on here. Here's the dashed line representing the median educational level. So as someone becomes more and more educated, the effect of experience diminishes. So as we go from the minimum amount of education to the median amount of education, in other words, education is increasing, the slope of the implicit regression line is getting closer to 0, implying the relationship between salary and experience is weakening. Eventually, between the median and the maximum, this slope is 0, implying the effect completely disappears. And at the very largest levels of education, it looks like experience maybe hurts you a little bit. The relationship is actually somewhat negative. So, same story that we got out from the equations, and same story that we suspected. There's an interaction between experience and education. The effect of education on salary diminishes as someone gets more experienced, and vice versa. The effect of experience on salary diminishes as someone gets more educated. So probably that didn't make all that much sense to you guys right now. Interpreting these interaction plots are very, very important, but it becomes easier with practice. You'll have to practice quite a bit. Okay, so when do we suspect an interaction? It's actually important to know when we suspect it based on the interaction plots, because when we have a lot of variables in the data set, the amount of interactions, the pairwise interactions, can be huge. So we should really be specifying the interactions that we might only really care about. So when do we suspect an interaction? Well, in this case, I would not suspect an interaction between x1 and x2. In fact, by design, I've set up y to be just a weighted sum of x1 and x2 without any interaction. And here's the resulting interaction plots. What we see is that the relationship between y and x1 has essentially a constant strength regardless of x2. The slopes of these three implicit regressions are essentially one and the same. In other words, the coefficient of x1 is the same regardless of x2, and that's what the multiple regression model is assuming without any interaction, so no interaction. These slopes are nearly parallel, so no interaction. Same thing over here. This is just looking at the same problem from a different angle, y versus x2. We see these three lines are nearly parallel. We would not want to incorporate an interaction between x1 and x2 because it looks like the effect of 1 on y is constant regardless of the values of the other value. When do we suspect an interaction? Well, when the slopes of those implicit regression lines look very different, especially if I see a crossing. So here I've designed y to actually have an interaction between x1 and x2. And so what I see is that, yes, the strength of the relationship between y and x1 is changing actually quite a bit as x2 changes. So the minimum value of x2 is this solid line. As x2 is getting bigger from the minimum to the median to the maximum, I see that the strength between y and x1 increases. The slope is getting farther from 0. This line is getting more tilted. All right. Same story, different angle here. How does the relationship between y and x2 change as x1 varies? Well, the relationship between y and x2 is slightly negative for the largest values of x1, and the smallest values of x1, that's the solid line. And as x1 gets bigger, what I see is that it goes from a very weak negative relationship to no relationship at all, a flat horizontal line, to slightly positive, to even more positive. So overall, it looks like that as x1 is getting bigger, the relationship between y and x2 is getting stronger. So if I see very obvious non-parallel lines, I would suspect an interaction to exist. Okay, so one additional thing about interactions before we go through another example is how we deal with them in the regression model. So there's this thing called model hierarchy that a lot of statisticians worry about. And model hierarchy is just about a very particular way that we specify the multiple regression model. In other words, keeping the model in a pleasing and logical form. And we've actually already talked a little bit about model hierarchy. When we had a polynomial model, we said that no powers of x can be dropped, even when the p-values are 5% or bigger. So if we have a polynomial term in our model, we keep all those powers even if they're not significant. That's one aspect of model hierarchy, keeping it in a nice logical form. And in terms of interactions, in order to preserve model hierarchy, no terms involved in an interaction can be dropped if you're including that interaction in the model. So a good model, one that preserves model hierarchy, would look something like this. I have a polynomial term in x2, and I've included x2, x2 squared, and x2 cubed. We preserve model hierarchy. Likewise, in this model right here, I have an interaction between x2 and x3, and I have the individual components of that interaction, x2 and x3 by themselves. That's a good model. It preserves model hierarchy. This would be a bad model that violates model hierarchy because you'll notice I have my x2 term and x2 cubed term here, but I'm missing the x2 squared term. I'm violating hierarchy here. And likewise, I'm violating model hierarchy here because I have the interaction between x2 and x3, but I'm missing the individual components, the x2 term and the x3 term in my model. Okay, so when we fit the interaction, there are conventions for including the components of the interaction as well. Likewise, there's a convention for keeping all the powers of x in the polynomial model. Okay, let's actually go back and look at the cars data set where we're predicting the fuel efficiency from the size of a car, horsepower, top speed, and weight. And in the previous chunk, we saw that there was a slightly nonlinear relationship between fuel efficiency, horsepower, and top speed. I'm going to ignore that for right now just to illustrate the interaction plots. So one thing I'm going to do is I'm going to fit a model with all of the interactions in it. So we'll talk more about how we actually do that in R, but twiddle dot, remember, uses all the variables. Twiddle dot exponent 2 is going to fit all the interactions as well. So I'm just going to look quickly at the summary, and we can see immediately, actually, that some of these interactions look to be important. Noticeably, the interactions that involve cab volume, the size of the car, are all highly statistically significant. So that implies that, you know what, my model probably stands to improve a little bit if I incorporate some of these interactions in there. Notice R squared adjusted has increased from the model with no interactions to the model with the interaction. So maybe interactions are a good idea. Let's explore what these interaction plots are telling us about the model. And so I'm going to run my command interaction.plots. I give it the name of my model. And in this case, I'm going to say many equals true because there's a lot of different interactions here. If I only have one, I can leave off that argument. All right, so let's look at this first set of interaction plots. Here is the implicit regression equations relating the fuel efficiency of the car to the size of the car for various values of horsepower. So we start out at the minimum horsepower at the solid line. We suspect an interaction because these slopes look quite a bit different. And the story that it's saying is that, okay, as I go from the smallest horsepower to the largest horsepower, it looks like the strength of the relationship between fuel efficiency and horsepower and cab volume increases because the slope is getting farther from zero. It's getting more and more negative. Okay, well, let's look at it from a different angle. What's the relationship between fuel efficiency and horsepower for various sizes of the car? Well, at the very smallest sizes of the car, it looks like the relationship between fuel efficiency and horsepower is a little bit positive. But as the size of the car gets bigger, it looks like the relationship between fuel efficiency and horsepower starts to become negative. So it kind of switches sign. That's what the data is saying. Let's look at the next set. Here, very strong interaction because we see the slopes of the implicit regression lines are very different. They cross. What's the story here? Well, we're looking at the relationship between fuel efficiency and cab volume once again, but for different values of top speed. So at the smallest top speed, at the solid line here, we see the relationship between fuel efficiency and cab volume is negative. Bigger cars, which have the same top speed, tend to have worse fuel efficiencies. However, as we go from the smallest value of top speed to the median top value, this relationship weakens because the slope is getting closer to zero. It's going from a fairly substantial negative number to something that's very close to zero. And then as we go from the median to the maximum, we start getting into a positive relationship, in fact, fairly strongly positive. So the story that this is telling us is that the relationship between fuel efficiency and cab volume gets smaller as the top speed of the car gets bigger and then starts to turn around and starts to strengthen and become positive for cars with very large top speeds. All right, same story, different angle here. Here's the relationship between fuel efficiency and top speed for different sizes of the car. For the smallest cars, the relationship between fuel efficiency and top speed is very highly negative. For the median value of car size, we still have a moderately negative, but not nearly as negative relationship. And by the time we get to the largest value of cab volume, it is somewhat positive. So the story that we can say is that the relationship between fuel efficiency and top speed diminishes as the car gets bigger up to a certain point, which all of a sudden it starts to increase and become positive. So it starts out negative, it diminishes as the size of the car gets bigger, and then starts to become somewhat positive for very large cars. All right, let's look at a few other plots. I would not suspect an important interaction between fuel efficiency and cab volume because the slopes of these lines are just about the same. There's not a huge difference. We saw actually in the multiple regression model that it was statistically significant, but not very practical significance because there's not much of a difference here. I would not suspect an interaction at all between horsepower and top speed because these three lines are all parallel. The effect of horsepower on fuel efficiency looks to be a constant in that regard. And same thing, no interaction between weight and horsepower. These three lines are about parallel. And then top speed and weight, I wouldn't really suspect a strong interaction either because the slopes of these three lines are just about the same. All right, so it takes a bit of practice to get used to interpreting the interaction plots, but you can start to see the power of why you would want to incorporate interactions into your model. Because in the real world, very often the relationship between y and x is not a constant, but it actually depends on the value of some other variable. So by adding in an interaction term, we allow for the possibility that the strength between y and x does indeed vary. And we can let the data tell us whether or not the interaction is significant. Do I need to allow the effect of x on y to vary? Okay, so last little bit, making predictions in the multiple regression context. It's just like simple linear regression where we get our best guess just by plugging in the values of our predictor variables into the regression equation. And the same procedure applies for getting confidence intervals and prediction intervals. We know that our best guess, what we get from plugging in the values of x's, isn't going to be equal to the truth, but it's going to be close. And when all of the assumptions behind the regression model are true, we can actually predict how far away our estimate is from the truth. That's what the standard error is. And so we can use predict once again to actually get prediction and confidence intervals. The one tricky thing here is determining whether or not you are extrapolating. So remember, extrapolation occurs when you're predicting at a combination of x values that you really haven't seen before. In a linear regression context, that meant that you were predicting at too large of a value of x or too small a value of x outside the range of x that were used to build the model. But in the multiple regression context, it's basically just making a prediction at a combination of x's that is highly unusual, something that you really haven't seen before. And it's actually remarkably difficult to detect extrapolation in a multiple regression context because it's really difficult to tell how unusual that combination of x's are. It very well might be the case that you have very typical values for each value of the predictor, but overall the combination of those x's that you're making that prediction at is very odd. So what do? Well, we actually measure the leverage of the point that we're trying to make our prediction at. Remember, the leverage is how unusual that point is with respect to the shape of the predictor data cloud. It tells you how far away it is with respect to the way the data has been collected here. And if that leverage is large, then you may be extrapolating. So visually, what's going on? Well, let's imagine our predictor data cloud looks like this. We've predicted y from x2 and x1, and here's the relationship between the x1 and x2 values in the data. Maybe we're predicting something based on someone's height and weight. Height and weight have a pretty strong association, so x2 might be height, x1 might be weight here. Okay, so we would not be extrapolating if we were predicting at a combination of x's somewhere in this ellipse here. We're pretty confident that this model is going to hold here because that's the range of x that we've seen. However, if I were to make a prediction at the start point, this would be extrapolating because this is at a combination that is very, very odd. I haven't seen a combination of x1 and x2 like this before, and so I'm not confident that my model is going to apply this far outside the range of x that I used to build the model. And detecting this is actually fairly difficult. Imagine I didn't have the foresight to actually look at the combination of x1 and x2s, and I just looked at the x1 and x2 values individually. Well, this starred point right here does not really have that unusual a value of x1. It's right at about 122.5, and there are 2 points that are bigger than that. So it's not that unusual in terms of x1, and it's not that unusual in terms of x2 either. x2 is right at about 58, and I see, once again, there's 2 values that were actually smaller. So this point doesn't necessarily stick out in terms of unusualness, in terms of x1 or x2 individually, but it does stand out in terms of the combination. And so that's why we need to look at the leverage, because the leverage is able to synthesize what the shape of the predictor data cloud looks like, and it tells you how far away that point is from the center with respect to the shape of that data cloud. So when you make predictions, be aware that you may be extrapolating and not know it if you just check the x values. You need to check that point's leverage, how unusual it is with respect to the shape of the data cloud. And that's it.